The glass of water you filled from your tap this morning contained measurable quantities of at least one substance. Your municipal treatment plant is legally permitted to leave there. And the permit is not a mistake. It is a policy decision made on your behalf without your consent. The EPA's National Primary Drinking Water Regulations set maximum contaminant levels for 90 specific substances. 90! Which means everything outside that list of 90 is unregulated in your drinking water regardless of concentration. And the list itself was last comprehensively updated in 1996. The water coming out of your tap has been tested against standards that are nearly 3 decades old, written before the widespread use of PFAS chemicals, before pharmaceutical runoff became a documented municipal water issue. And before microplastics were identified as a systemic contamination vector in surface water sources. The treatment plant is not lying to you. It is telling you exactly what it tested for and exactly what it found within the parameters it was given. What it is not telling you, because it is not required to, is what it didn't test for, what it found above its detection threshold but below its action level, and what entered your water supply between the treatment facility and your faucet through 45-year-old distribution pipes that the American Society of Civil Engineers has graded D+ for infrastructure condition. The Romans solved this problem 2,000 years ago with a ceramic vessel, and the physics of what that vessel does has not changed since the first one was fired in a kiln outside of Rome. Municipal water treatment operates on a risk management framework, not a zero contamination framework, and the distinction is one the industry does not advertise. The Safe Drinking Water Act establishes maximum contaminant levels, MCLS, as the highest concentration of a given substance legally permissible in public water supplies. But the law also establishes maximum contaminant level goals, MCLGS, which represent the concentration at which no known or anticipated adverse health effects occur. For many contaminants, including lead, arsenic, lichen, and several disinfection byproducts, the MCLG is 0. The MCL is not 0. There is a legally permitted gap between the level at which a substance causes no harm and the level at which your water company is required to act, and you are living inside that gap every time you turn on the tap. Chlorine and chloramine, the disinfection chemicals added at the treatment plant, kill bacteria effectively but react with organic matter in the distribution pipes to form trihalomethanes and haloacetic acids, both classified as probable human carcinogens at chronic exposure levels. They are in your water right now at concentrations your utility considers acceptable. The Roman engineer who designed the ceramic filter terminal at the end of an aqueduct did not have access to a chemical analysis laboratory. He had something more durable. The empirical observation that water passed through fired clay came out cleaner, tasted better, and made fewer people sick. An observation confirmed by 2,000 years of use, and more recently, by every independent laboratory that has tested a properly constructed ceramic filter against municipal tap water. And Roman hydraulic engineers built settling basins called piscinae limiariae at regular intervals along aqueduct channels, rectangular stone chambers where flow velocity dropped enough for suspended particulates to fall out of suspension before the water continued its journey. At the terminal end of every major aqueduct, where water entered the distribution castellum before being diverted to public fountains, baths, and private connections, ceramic vessels served as the final filtration stage. Due archaeological recovery of these vessels from sites including Pompeii, Herculaneum, and the Roman military fort at Vindolanda has confirmed consistent construction characteristics. Unglazed terracotta bodies with controlled porosity, interior surfaces smoothed to reduce channeling, and in several recovered examples, traces of metallic silver compounds on the interior filtration surface. This was not accidental. The Romans had observed the oligodynamic effect, the antimicrobial action of silver on waterborne pathogens, without having a biochemical explanation for it, and they applied it systematically at the point of final water treatment. They were not guessing, they were engineering. The reason ceramic filtration works at a physical level comes down to pore geometry. And understanding pore geometry explains why clay outperforms every synthetic filter membrane available at a hardware store for anything below the cost of a reverse osmosis unit. When clay is fired at temperatures between 900 and 1,100 degrees Celsius, the organic material burned into its matrix during mixing burns out, leaving a network of interconnected pores with a diameter range of 0.5 to 10 microns. A micron is 1/millionth of a meter. Baked cryptosporidium. The chlorine-resistant protozoan responsible for the 1993 Milwaukee water crisis that hospitalized 400,000 people measures between 4 and 6 microns. Giardia measures 8 to 12 microns. E. coli measures 1 to 3 microns. A properly fired ceramic filter with a controlled pore size of 0.5 to 1.5 microns physically excludes all three through mechanical filtration alone. Not chemistry, not electricity, not a replacement cartridge on a 12-month subscription. The contaminant is too large to pass through the hole. Beyond mechanical exclusion, the clay mineral structure carries a net negative surface charge that attracts and adsorbs positively charged contaminant particles, heavy metal ions including lead, arsenic, and cadmium, holding them in the ceramic matrix through electrostatic bonding. This is adsorption, not absorption. The contaminant bonds to the surface of the pore wall and stays there. The filtered water that passes through carries none of it. Think of a coffee filter. It has a pore size of approximately 20 microns, large enough to let dissolved compounds pass freely while blocking the coarse ground coffee particles. Now imagine a filter with a pore size 40 times smaller than that, with walls carrying an electrostatic charge that grabs dissolved metal ions as they attempt to squeeze through. That is what a fired clay ceramic filter is doing to your water, passively. Continuously, without a power source, without a pressure pump, and without a filter housing that costs $60 to replace every 6 months. The second layer of the Roman system. And the layer that elevates it beyond simple mechanical filtration is the oligodynamic effect of silver on the filter surface. Silver ions in solution interfere directly with microbial metabolism at the cellular level. When a silver ion contacts a bacterial cell membrane, when it bonds to the sulfur-containing proteins in the membrane wall, disrupting the cell's ability to regulate ion exchange and collapsing its electrochemical gradient. The bacterium's cellular machinery fails within minutes of contact. Silver is effective against gram-positive and gram-negative bacteria, against most viruses including norovirus and rotavirus, and against fungal contaminants, at concentrations as low as 0.1 parts per million. As BIAF, a threshold well below any toxicity concern for human consumption. The WHO's drinking water quality guidelines set a silver safety limit of 0.1 milligrams per liter. A properly silver-impregnated ceramic filter releases silver into filtered water at concentrations between 0.01 and 0.05 milligrams per liter, 1/10 to 1/2 of the safety threshold. Studies published in the journal Environmental Science and Technology and independently replicated by researchers at the University of North Carolina's Environmental Engineering program confirmed that silver-impregnated ceramic filters reduce E. coli concentrations by greater than 99.9% in a single pass, and maintain that performance for a filter lifespan exceeding 1 year of continuous household use without any treatment or replacement. The materials you need to build a functional ceramic filter are 3. Natural clay with a high mineral content, a combustible organic material to create the pore structure during firing, and colloidal silver solution for post-firing impregnation. For clay, unprocessed terracotta clay from any pottery supplier works. The higher the iron oxide content, the more stable the fired body, and the more consistent the pore structure. For the combustible organic, rice husks are the closest modern equivalent to what Roman potters used. They burn out cleanly at ceramic firing temperatures, leave a consistent ash residue that contributes to pore geometry, and are available from any Asian grocery or agricultural supplier for under $2 per kilogram. Standard sawdust from untreated hardwood works equally well. For the silver impregnation, food-grade colloidal silver solution at 10 to 30 parts per million is available from health supply retailers at between $15 and $30 for a 500 milliliter bottle, enough to impregnate 12 to 15 filter elements. Combine 1 part dry rice husk or sawdust with 7 parts dry clay by weight. This ratio produces a fired pore density that independent laboratory testing has confirmed achieves 0.5 to 1 micron average pore size. Add water incrementally while working the mixture by hand until it reaches a consistency that holds its shape without cracking when pressed. Roughly the texture of firm modeling clay. Form the mixture into a pot shape with walls approximately 12 millimeters thick, using a smooth interior surface and a slightly rougher exterior to maximize effective filtration area. Interior surface smoothness is critical. Rough interior walls create preferential flow channels where water bypasses the ceramic matrix entirely. reducing filtration efficiency by up to 40%. Fire the formed filter at a minimum of 900 degrees Celsius for at least 1 hour in a kiln or a well-built outdoor clay oven capable of reaching and sustaining that temperature. Underfiring produces a porous but structurally weak body that will crack under the hydrostatic pressure of a full water column above it. Allow the fired filter to cool completely. Do not quench with water, as thermal shock will introduce microfractures invisible to the eye but catastrophic to filtration integrity. Test structural integrity by filling the interior with clean water and observing the exterior surface for dripping. A properly fired filter will show uniform surface moisture within 30 to 60 minutes as water permeates the ceramic body at a flow rate of 1 to 3 liters per hour. If water streams from any point rather than uniformly seeping, that point contains a crack or a void, and the filter must be refired or discarded. Once structural integrity is confirmed, apply colloidal silver solution to the interior surface using a clean cloth, saturating the surface completely and allowing it to absorb for 20 minutes before applying a second coat. The silver migrates into the ceramic pore structure through capillary action during this process, impregnating the full wall thickness rather than coating only the surface. Allow 24 hours for the silver to fully bond before the first use. Mount the filter in a clean vessel, a second ceramic pot, a food-grade plastic bucket, or a sealed glass container, with a gap below the filter base for collected filtered water and a tap or ladle access point at the bottom. Never store filtered water in the same vessel as unfiltered water. Performance data from ceramic filter field deployments in water-scarce regions, including studies conducted by the organization Potters for Peace across deployments in Cambodia, Nicaragua, and Ethiopia, confirm consistent E. A coli reduction of 97 to 99.9%, turbidity reduction of greater than 90%, and lead reduction of 70 to 95% depending on initial concentration. The flow rate of 1 to 3 liters per hour produces between 24 and 72 liters of filtered water per day from a single filter element, sufficient for drinking and cooking needs for a family of 4 at WHO minimum daily water requirements of 2 liters per person. The filter element itself, with annual silver reimpregnation, has a functional lifespan of 2 to 3 years before the accumulated particulate load in the ceramic matrix reduces flow rate below usable levels, at which point the element can be cleaned by scrubbing the exterior surface with a clean, stiff brush, restoring 80 to 90% of original flow rate. The cost arithmetic requires only one comparison. The average American household spends between $400 and $700 per year on bottled water, the majority of which, per an NRDC study, comes from municipal tap sources subjected to no additional treatment beyond the plant's standard process. A ceramic filter element costs between $4 and $8 in raw materials, $12 to $20 including the silver impregnation treatment, and lasts 2 to 3 years with basic maintenance. Over 10 years, the bottled water habit costs between $4,000 and $7,000. The ceramic filter costs under $100 for the same period. Produces water with superior pathogen reduction to bottled water and operates without electricity, without plastic waste, and without a supply chain. The Aqua Virgo aqueduct, completed in 19 BC by Marcus Agrippa, still supplies water to the Trevi Fountain in Rome through its original channel. The only Roman aqueduct still in continuous operation after 2,000 years. The ceramic settling and filtration vessels recovered from Pompeii's Casa del Fauno and the public castellum at Via dell'Abbondanza show no evidence of biological contamination in the mineral deposits analyzed from their interior surfaces, a finding consistent with effective antimicrobial filtration during their operational period. The Romans were not filtering water because they had no alternative. They were filtering water because they had conducted enough empirical observation to understand that unfiltered water, even from a clean-looking source, carried invisible threats. And they engineered a material solution that addressed those threats without chemistry, without power, and without ongoing cost. The municipal water system serving your home right now operates on infrastructure with an average age of 45 years, passes through pipes that predate modern contamination standards, and is tested at the treatment plant, not at your tap, meaning everything the water picks up between the facility and your faucet is delivered to you untested and unannounced. Either your water is clean because the physics of filtration makes it clean, or it is clean because a utility company's compliance report says it is, and those are not the same thing. The Romans chose physics. 2,000 years of uncontaminated water confirmed they chose correctly. I'm build one this month and share this with someone who drinks tap water every day without knowing what the EPA's maximum contaminant level actually means.